Okay, fellas, today is the Chapter 8 Rotational Motion walkthrough. So let's just start up on the first question. You have 13 questions on this homework. Let's open it up. Okay, so the first one just has a bunch of angles, and it says convert them into radians, right? Okay, so let's see how would we do this. Okay, so a circle has how many degrees? 360 degrees, right? How many radians is in a circle? Remember, that is 2 pi radians. So if a full circle's 2 pi radians, then if you split it in half, like 180 degrees, that would be pi radians, right? Pi radians would be in half. If you did it in half again, like at 90 degrees, it would be like pi over 2 radians, right? So how would you go about like switching any of these? Whoops, where is it? How would you go about like switching any of these? So I would personally say you can bring up like an image of a unit circle. Like if you bring up an image of a unit circle, I'm sure you guys have one from calculus. You can just memorize them. Like 45, 60, 90, 360, 445. These first four are super easy. Yeah, the 445 is a little different. Let's see how we would convert something. Let's make up a different one. Let me pause it so I grab one that makes sense. Okay, I'm back. So let's say we just grab like 600 degrees. And we say, hey, I'll switch that over to radians. Okay, well, I mean, if you know your conversions, you should be good at this. So remember, in order to cancel stuff out, you would want to put the thing that you want to cancel out on the bottom. So you want to cancel out degrees. So just think of any degree you could use. You could do like 360, you could do 180, whatever it is. So you cancel out degrees. And then however many radians are in 360 degrees, which would be 2 pi, right? And there we go. You could also, if this one's easier, you could do 600 degrees times pi over 180, right? Because 180 is pi, and that cancels out the degrees as well. And then you can just multiply them in your calculator, get what the answer is, and you're good to go. Okay, so that's how you do conversions there. I highly suggest memorizing the easy ones, like 45, 60, 90. Those should just like come to mind. Like if you're doing it on like in calculus or something, it should just be there in your brain. Okay, a grinding wheel is 0.36 meters in diameter and rotates at 1,700 rotations per minute. Okay, calculate its angular velocity in radians per second. Radians per second. Okay, so they gave me a diameter and they gave me a rotational speed, that is omega, right? Except omega is written in radians per second. This is in revolutions per minute, or rotations per minute, right? Okay, so let's kind of mess around with this. Let's come up with different numbers. Let's say I got something rotating at like 600 revolutions per minute, and it has now remember, what I care about is radius. So they gave diameter over here. You don't want that. You want to divide that by 2. You want to be given the radius. Let's say the radius is like 0.10 meters, yeah? Make sure it's in meters, yeah? You never want it in anything else. Okay, first thing is rotations per minute. I don't want it in rotations per minute. I want it in radians per second. So let's figure out how we would convert that. So we got 600 rotations per minute. And just like we were canceling out stuff earlier, okay, you can memorize this. But I want to cancel out minutes. I want to make it seconds. So I'm going to put minutes on the top so that they'll cancel. I want to switch it to seconds. And I know that 1 minute is 60 seconds, right? So if I do 600 divided by 60, now it's in rotations per second. Now I want to switch it from rotations to radians, right? So I'm going to put rotations on the bottom and radians on top. And 1 rotation, right, is equal to 2 pi radians, because 1 full circle is 2 pi. So in order to switch anything from revolutions per second or rotations per second, however you want to say it, it's just going to be 600 times 2 pi over 60. And that'll switch it to radians per second. So let's see what that is real quick. 600 times 2 pi over 60. I hate how long it takes the calculator to load. Okay. 600 times 2 pi over 60. That comes out to 20 pi. Man, it came out so nice. I just made up that number. 20 pi radians per second. Yeah? And then, I mean, on here, they want it in 3 significant figures. So you're not going to want it in 20 pi. You're going to want it in, you know, a decimal. And 3, it said 3 significant figures, I think. That'd be 62.8 in this case, right? And yours, you know, make sure you do it with whatever numbers you have. Okay, and then it says, what is the linear speed of a point on the edge of the wheel? So remember, in order to switch between linear and angular, you got to have that formula, yeah? And that formula is V equals omega times R. And you can do it on any of these. So A is equal to alpha times R. It switches them. And if you like, you can even do like distance. Distance is equal to however many radians it went times R, which is the radius, right? So these are the things to switch from angular to linear. Okay? So in this case, you just do like, in my case, I have 20 pi as my omega times R, which would be that. So in this case, it'd be 20 pi or 62.3 or whatever it was, 62.8. 62.8 times R, which my R was 0.10. I got my answer of 6.28, you know, and then it's now in linear, so it wouldn't be radians per second, it'd be meters per second, right? Meters per second. So it'd be 20 pi times 0.10, and that would be, what was it, 6.28 meters per second, because now it's a linear distance, okay? And then what is the acceleration of a point on the edge of the grinding wheel? Well, think about it. It's moving at a constant. It doesn't say constant, but it tells you how fast it's moving, right? So it's moving at 1,700 revolutions per minute. Doesn't seem like it's accelerating at all. Seems like it has a constant velocity. Okay? Let's look at the next one here. The blades in a blender rotate at 7,000 rotations per minute. So remember, you got to switch that over to radians per second. So multiply by the 2 pi over 60, right? When the motor is turned off during operation, the blades slow to a rest in 2.5 seconds. What is the angular acceleration of the blades as they slow down? Okay, so let's remind ourselves of the formulas. Yeah, so here we have these 3 to switch linear and to linear from angular. But let's also write down our old formulas. Remember our old formulas: x equals x naught plus v naught t plus a half at squared. Remember, these are the first things that I ever taught you guys. Plus at vf squared equals v naught squared plus 2a x minus x naught. Okay, and then remember, you can switch all of these two angular things. The linear, the distance would be theta equals theta naught plus omega naught t plus a half. Whoa, that's a half. Alpha t squared. Yeah. And then omega f equals omega naught plus alpha t. This last one would be omega f squared equals omega naught squared plus 2 alpha theta minus theta naught. Yeah? And that gives you all the angular stuff. There we go. Looks good. Looks set. Okay, so we are going to use one of these, you know, to find this. Let's write down the stuff that we know. The blades in a blender rotate at 7,000 rotations per minute. first off, switch it to omega, to radians per second. But that is your omega naught, right? That's what it's spinning at. So we do know that. It's turned off during operation. The blade's slow to a rest. So they slow down to a rest, which means you know the final velocity. And it took 2.5 seconds. So you have time. And then it wants, I mean, you have time. I don't know why I put a question mark. It's 2.5. And then it wants the acceleration, right? So with those three givens, you should be able to find what formula you're using to get acceleration, angular acceleration. Okay. Let's keep going here. A cooling fan is turned off when it is running at 930 revolutions per minute. You know how to switch it. It turns 700 revolutions before it comes to a stop. What is the fan's angular acceleration? Okay, so let's just look at this. You're given your angular velocity, the initial one, yeah? Cooling fan is turned off when it's running that fast. It turns 700 before coming to a stop. So you know its final velocity. 700 revolutions, that is something you know, so you need to write it down as a known. But it shouldn't be in revolutions, it should be in radians, right? So if it's 700 revolutions, you would want to do like 700 revolutions divided by 2 pi, whoops, 2 times pi, and that's how many, here, let's switch it to, I need to go grab it. Let's switch it to a decimal. That's how many radians it traveled through. Yeah, so that would be, you know, theta. Yeah, so they gave you omega naught. You know what omega f is because it came to a stop. You know that the beginning was 0. You know, it had traveled 0 radians. Then at the end, you know it had traveled, you know, in my case, 111.4. 111.4? That's not, yeah, 111.4 radians. Yeah, and then it wants you to calculate, what does it want? The angular acceleration. So you should be able to look up here and see what you can use to calculate the angular acceleration. Then how long did it take to, then you need a time, right? There we go. You should be all right. That one, that point. A 52 kilogram person is riding a bike, puts all her weight on each pedal when climbing a hill. The pedals rotate in a circle of radius 18 centimeters. So remember that is 0.18, right? You need to make sure it's in meters. So 0.18 meters. What is the maximum torque she exerts? Okay, so think about this. Let's do a little drawing here. A person is rotating a pedal. Think of this as the circular motion of a pedal. And they push down, right? When you're trying to ride a bike, you're pushing down on the pedal. Well, where would it give maximum torque? It'd give maximum torque right here, right? Because then it pushes the hardest down. Because it's when the radius, it's pushing perpendicular to where the thing is, the pedal. So the maximum torque would occur right there. And then you want to figure out, what was it? What is the maximum torque? Well, just remember your formulas for torque. Yeah, here, let's bring them up real quick. Torque is the little, it's a tau. It's a lowercase tau. So it could be force times radius. So think about it. If somebody's applying their weight onto it, you got to calculate the weight because that'll be your force, and then times the radius of the pedal. And that'll tell you, you know, the torque that you have. Okay. I thought there was another, oh yeah, there's another torque formula here. This is not the one you're using, but remember torque is also, you can write it as moment of inertia times alpha. Yeah, which is angular acceleration. If you multiply I over. Okay. Next one. What is this? Okay. A wheel that is initially at rest has forces applied to it, as shown here. It begins to rotate. Begins to rotationally accelerate. Calculate the net torque on the axle of the wheel shown in Figure 1. Assume that friction, torque of 0.55, opposes the motion. Okay, so let's look at this. So you can see that two of them, this one, the 35 Newton and the 18 Newton, look to be moving in the same, clockwise direction, while the 28 Newton looks to be moving in the opposite clockwise, the counterclockwise direction, yeah? So let's count clockwise as positive. So get the torque coming off of the 35 Newton. Remember, a torque is force times radius, right? So you're going to do the force times the radius. Make sure your radius is in meters. And then add it with all torques that, go clockwise. Then subtract all torques that go counterclockwise. Yeah? And it also has a torque of friction that's opposing motion. So it looks like if it's moving counterclockwise, we should subtract off the 28 one and subtract off the friction. Okay, so subtract off both things. And then on the friction, you don't need to multiply this with the radius or anything because remember, it's being applied right at the center, so you don't need to multiply it by radius. And this is already in torque, the unit's already torque, so, Newton meters. Okay, let's go to the next one. Okay, the solid dot showing in the pivot points, the board can rotate about the pivot. Okay, which force shown exerts the largest magnitude of torque on the board? Okay, so here's the pivot point, right? So which one of these torques is going to make the door move with maximum speed is a way of thinking about it. Which one's going to apply the most torque on it? So remember, torque is force times radius. So which one is applying a force that is perpendicular to the pivot point and rotates around and has the largest distance from the pivot point, because that's force times distance. Okay. To the next one. Determine the moment of inertia of a 12.4 sphere of radius this when the axis of rotation is through its center. Determine the moment of it. So remember, moment of inertia has a ton of formulas. Ton. You would have to look at them all. Moment of inertia formulas. And, it's for different shapes. Okay, so let's see here. Let's just go to images. Check it out. There's just tons of them. Lots of different formulas, depending on what the shape is or what it's rotating around. So you would want to make sure you find the one that it's talking about. So let's look at this one. It says determine the moment of inertia of a 12.4 sphere of radius 0.66 meters when the axis of rotation is through its center. So it's a sphere that's rotating through the center. Yeah? So it looks like a ball rotating through the center. So it doesn't tell me if it's, I'm just assuming it's solid. It doesn't say. Okay, so I'm going to assume it's a solid sphere and it's rotating through the center. These all look like they're probably through the center, but they don't show an axis of rotation. But so a solid sphere is 2/5 mr squared. So you would just do 2/5 times m times r squared. And there you go. Okay, next one. Estimate the moment of inertia of a bicycle wheel that is 67 centimeters. Make sure to switch that to meters. In diameter. Don't get confused. Remember, everything is radians. Radius. The rim and tire have a combined mass of 1 kilogram. Okay, so we know the mass of the tire, and we know it's a bicycle wheel with some radius, and we want the moment of inertia. So you'd come over to your stuff, and you'd look for, it looks like probably a, I don't see it on here. Let's see. Something like this. A hoop. Probably this, and it rotates around the center. Because you wouldn't want a hoop that rotates like this. That's not how a wheel, goes around a bike, right? So it would be this one. So it'd just be mr squared, I believe. So it'd just be mr squared. So it'd be mass times radius squared. Make sure to use the correct units. If you don't remember the correct units, go back to the previous one. It has some units on there. Yeah? For moment of inertia. Moment of inertia. There you go. Yeah? Okay, so that's how you'd calculate I. The mass of the hub at the center can be ignored. So they're saying that the bicycle wheel has a kind of center hub spot where the axle goes through. to make it spin, saying, why can you ignore it? So I'll let you guys take your guess on it. A merry-go-round accelerates from rest to 0.65 radians per second in 35 seconds. Okay, so this, I mean, when I read that, I'm thinking it's probably something, back to our old formulas. Okay, so the things that we know so it starts from rest, so we know initial angular velocity, so omega naught. We know omega f, which is how fast it's moving afterwards, and we know time. So assuming the merry-go-round is in uniform disk of radius 7 meters and a mass of that, calculate the net torque required to accelerate it. Okay, so first off, on this one, it looks like we're probably using this formula, the torque formula right here. So let's look at that formula real quick. So torque is equal to, I messed this up. Alpha, angular acceleration, is equal to torque divided by I, which means if you want torque, you can do moment of inertia times acceleration. Yeah? Let's see what the formula is asking about. So it says you have a uniform disk of radius r, and it's a merry-go-round. So what I'm thinking about is it's something like this solid cylinder. Yeah, and it's rotating around the center like this one, because it's just, it's horizontally. This one's showing it, horizontally, but we got to think about it vertically. Okay, so it looks like to get the moment of inertia, I would do a half mr squared. So I would do a half mr squared to get I, and then wants to know what the net torque is. So I need to know what the acceleration is. So I would have to use this stuff to calculate the acceleration. So use our old formulas to calculate the acceleration based off of this stuff that we have. Then use this formula to calculate the torque. So you're going to calculate the acceleration from one of these formulas. Then you're going to calculate the moment of inertia by a half mr squared. And then you're going to multiply I times alpha, and that tells you torque. Yeah, and torque's in Newton meters. Okay, next one. Helicopter rotor blade has a thin rod. Okay, so he has these 3 thin rods. Okay, if each of the 3 rotor helicopter blades are 3.75 meters long and has a mass of 135 kilograms, calculate the moment of inertia of the 3 rotor blades of the axis rotation. So we got these 3 rotor blades. They spin around the center, right? So I'm just going to do one of them. Just focus on one blade. And then we get the moment of inertia of it and multiply it by 3 because there's 3 blades. Okay, so I'm thinking like this one right here. The rod about its end. Because you can think of this as the one rotor blade, and it rotates around this middle point right here. So the moment of inertia is going to be 1/3 ml squared. So 1/3 times m times, L squared, which is the length of the blade. And then multiply that by 3, and you'll have your total moment of inertia. How much torque must the motor apply to bring the blades from rest, so initial velocity of 0, to a speed of 3, so final velocity, time is that. So how much torque is needed? So now you have the moment of inertia, just like we did in the last one. Calculate the acceleration you're going to need, the angular acceleration, using your old formulas, and then just do I times alpha, right? This is very similar to the last one. Okay, a centrifuge motor rotor has a moment of inertia of that. So we know what I is. How much energy is required to bring it from rest to that speed? You know what? On this last one, this is in revolutions per second. So make sure to switch this to radians. Yeah, so you're going to multiply it, or multiply by 2 pi, right? You got to have it in radians per second. Okay. How much energy is required to bring it from rest to this? So revolutions per minute. So remember, multiply it by 2 pi over 60 to switch it to radians per second. And you know it started from rest. How much energy is required to bring it from rest to this speed? So we're going to use centrifuge, we got the I, and it wants to know how much energy it takes. So I would go over to my formulas. Energy, angular energy, would be right here. Yeah? So it's a half I omega squared. So I'll do a half times I times omega, which is this one. That's how fast it's moving, squared. Just make sure to put it in radians per second. Okay, last one here. That is, can't even read it. Okay, what is the angular momentum of a 0.305 kilogram ball rotating around the end of a thin string in a circle of radius 1 at an angular speed of that? So what is the angular momentum? Okay, so let's look at what the formula for angular momentum is. Look, it is I times omega is the one I would be focusing on. I times omega. I need to figure out the moment of inertia, then multiply it with the angular speed. Looks like the angular speed is 11. So I need to figure out moment of inertia, and then I'm good. Now it's a ball rotating around a thin string, so the ball's flying around, you know, like this. So let's figure out which one that would be. These are like spheres rotating around their center axis. That would not be it. We need a ball rotating around like this. I just saw it a second ago. Yeah, there it is. So like this is a ball rotating around a sphere with a string. So it's going to be I as mr squared. Mr squared is just how you would calculate it. So to calculate I, it would be mr squared, and then you would multiply it with your angular velocity, right? Okay, that's all of them. I hope it made sense. Have a great day. Adios.